Hello, everyone. Today for lecture, we will be covering chapter 1, which is based on measurement, matter and measurement. And later we'll also be talking about atoms and the periodic table. So we're going to start as very broad and then narrow down into atoms. And today we'll just be talking about chemistry and why we study it. And this will be really helpful as we go through the rest of the semester and understand compounds and chemical reactions, then relate them to biomolecules such as proteins and DNA and fats and lipids, and then end with metabolism and how our body takes all these macromolecules and breaks them down for energy for our body and other things. So chemistry is the study of matter, its composition, properties, and transformations. And when we talk about composition, we're going to talk about the arrangement, type, and number of compounds or molecules that make up a substance. And matter is anything that has mass and takes up volume and space. In today's class, we will discuss the states of matter, the classifications of matter, and then we'll talk about ways that we can measure matter with some examples along the way. First, we must define composition and structure, as that's something that we like to study in chemistry. Composition is the type and number of components or molecules that make up a substance. And then structure is how those components are arranged and held together. And there are two different things. We'll explore them using the molecule of water shown here. You can see that the composition of water is 2 hydrogen molecules, which are denoted by these white blobs here, and then 1 oxygen molecule, which is the big red circle here. But then when we talk about structure, we're going to actually talk about how those atoms are arranged and held together. So the structure of water is a hydrogen on the left, an oxygen in the middle, and then a hydrogen atom on the right. If they were in another structure, they would be a completely different molecule. So review again, composition is what molecules are in the actual, what atoms are actually in the molecule, and then the structure is how they are connected together. Now we're going to talk about the states of matter, and we'll use water again as our example. There are 3 states of matter: a gas, a liquid, and a solid. And a solid is rigid, it has a definite volume, and it maintains the shape regardless of container. And the particles lie close together. So an example of a solid, if we use water, is ice. And so you can pour water into an ice cube tray, put it in the freezer, and it will form a solid shape. And if we take the ice cubes out of the ice cube tray, they still will maintain that square shape. So regardless of whether it's in the container or out, it maintains its shape and it's rigid. And you can see here in this example that the water molecules shown in blue are highly compact and rigid. Next, we'll talk about the state of matter that's a liquid. This also has a definite volume, but it takes on the shape of a container. So if we go back to our water example, when we pour water into our ice cube tray, now it has the shape of the ice cube tray. If we take the water out of the ice cube tray and put it into a cup, then it will take on the shape of the cup. Now, even though it has the ability to take on the shape of a container, the volume will remain the same. The particles are close together, but they can move around randomly. So in our example here, we have a little flask filled with some blue water molecules, and you can see that they're not as closely together or compact as the solid, and they're able to move around each other. Lastly, we'll talk about our third state of matter, which is a gas, and it has no definite shape or volume. The particles can move randomly and are spaced far apart, and they will take the shape of a container. So we do have things called compressed gases, and they can fill up a container. If you're in a room, it's filled with gas or air molecules, and you can see that there's no definite shape, and these molecules can move around. There's no rigid structure. So here in this cloud, they're kind of all over the place. But if you did need to, put the lid on a jar of air, it would take the shape of that container. So after we define the states of matter, we're going to talk about some properties of matter. And we're going to talk about first the physical properties. And these are those that can be observed or measured without changing the composition of the material. Remember, the composition is exactly what atoms make up that matter. So when we talk about physical properties, we're going to talk about physical changes as well. And these physical changes alter a substance without changing the composition. And we'll use water again as our perfect example. So the composition of water, as a reminder, is 2 hydrogen atoms and 1 oxygen atom. And we can start with ice. Again, solid, rigid structure, compact molecules. And if we add energy and melt the ice, we form water. Now you can see that the composition has not changed. There's still 2 hydrogen atoms and 1 oxygen atom. However, now we're in a liquid state of matter and the molecules can move around more freely and will take the shape of whatever container it's filling. If we add more energy or heat things up, like when you boil water, you can see that you'll form vapor. That's called evaporation, and you'll get water vapor or steam or water gas. And you can see here that even though now we have fewer molecules that are more freely moving in this container here, the composition has not changed. It's still 2 hydrogen atoms here in white and 1 oxygen atom here in the red. And the structure hasn't changed at all either. You can see that there's still 1 oxygen atom in the middle with 2 hydrogens on either side. Now, in addition to physical properties, we have chemical properties, and those chemical properties can be determined. Chemical properties are those that determine how a substance can be converted from one form to another via a chemical change or what we call reaction. And we will have an entire chapter talking about chemical reactions and how we can convert one substance to another. We'll use water again as our reaction, and we can see here that we have a chemical equation where we have reactants on the left and our product on the right. And to form a water molecule, we have 2 of these hydrogen atoms here, and then 1 of these oxygen molecules. And through a chemical change or chemical reaction, we form the water molecules that we've discussed the composition and structure of in the previous slide. So you can see here that we've gone through a chemical change because we've converted this hydrogen and oxygen into an entirely new substance, which is water. So now that we've talked about the different types of changes, we're also going to classify matter even further into a mixture. So a mixture consists of 2 or more substances. They can have a variable composition, so what they're made of, and mixtures can be separated by physical means that there's no type of chemical reaction or chemical change that needs to occur. And mixtures occur in 2 types. We have homogeneous mixtures, and these are properties, or the properties are uniform throughout the mixture. And then we also have heterogeneous mixtures where the properties are not uniform throughout the mixture. And we're showing an example here. You can see that a heterogeneous mixture of both these pink dots and green dots, we have more of the pink dots on this side of the mixture and more of the green dots on the other side of the mixture. So this isn't very uniform throughout. There's a separation. An example of this would kind of be like oil and water. They don't really mix very well, but they're put together in the same container. A homogeneous mixture, however, has the molecules more evenly distributed. So you can see here, you have 1 pink molecule, 1 green molecule. So if you were to take a sample of this homogeneous mixture, then you could see that you would probably have a chance of picking out an equal amount of pinks and greens versus this heterogeneous mixture where if you pick some out, depending on where you picked out, if you picked out from the top, you pick out more pink. If you picked out from the bottom, you pick out more green. Now that we've talked about a mixture, what exactly is a pure substance? So pure substances have a definite composition, and pure substances cannot be separated by physical means. And there are two types that we'll explore in this class, which are elements and compounds. Elements cannot be broken down into simpler substances by chemical means. And in this presentation, a little bit later, we'll talk more about the elements, but you all may be familiar with the periodic table, and this is where you find the elements. There are approximately 110, and there are three groups of elements: metals, nonmetals, and metalloids, and we will discuss this in chapter 2. Compounds can be broken down into simpler substances by chemical means. They are a combination of elements in a fixed proportion by mass, and they're only separable by chemical reactions. These compounds are elements that are held together by bonds that can be created or broken by chemical reactions. So here is an example of separating elements and compounds. So these are elements. On the left, we have helium and oxygen, and you cannot break down helium any further. We'll talk in chapter 2 about what makes up an atom, but you can't separate them even by chemical means. The same with oxygen here. But a compound, like water, is a combination of 3 different molecules, and they can be broken down by chemical means. So to help with the classification of matter, let's say for an exam, you get asked about a particular a question of, classify this substance. First, you will ask if there's only one type of substance present in this matter, or more than one type of substance. If there's more than one type of substance, then we'll say that it's a mixture. And then once you have a mixture, you'll ask, is it uniform composition? If yes, it's a homogeneous mixture. Is it an irregular composition? If yes, then it's a heterogeneous mixture. On the other end, if you have some matter that's only one type of substance is present, then we'll say it's a pure mixture. If it's one type of atom, then it's an element. If it's made up of more than one type of atom, it's a compound. So let's do practice. We have this following image here, and we'll say what state of matter are these molecules in, and are the molecules a mixture or a pure substance? If it's a mixture, is a homogeneous or heterogeneous mixture? If it's a substance, is it an element or a compound? So we will say that this mixture is in a liquid state. The molecules of a mixture are a pure substance. This is a pure substance. You can see that there's only one type of molecule here. If you recognize from earlier, these are water molecules. If it is a mixture, which is not, we would talk about whether it was homogeneous or heterogeneous, but it's not. Instead, it is a pure substance. And because the substance is made up of 2 hydrogen and 1 oxygen, so more than one type of atom, we will say this is a compound. So now that we've kind of classified our matter, now we're going to measure it. And this will be important as we go through and talk about atoms and their weight and compounds and chemical reactions. It's really important to be able to describe matter as measurements. So every measurement has a unit and a number. For example, we will see here length. And let's say we have a piece of wood and the length is 21 inches. 21 would be the number and inches is the unit. And although here in America, we tend to use a different system of measurement, the metric system is used predominantly by scientists and healthcare professionals, and therefore we will be using it in this course. So each type of measurement in the metric system starts out with a base unit. So this is the quantity that we're going to measure. This is the metric base unit, and then here is the symbol. So when we want to describe the length of something or how long a piece of matter is, the base unit is a meter. If we want to say how much mass an object has, that gets measured in grams. When we talk about volume or how much space matter takes up, that will be described as liters. And when we want to talk about time or how long something takes, that base unit is in seconds. And the symbols here below for each unit. And then all units are related to the base unit by a power of 10. We'll describe this in the upcoming slides. And the prefix of the unit name indicates whether the unit is larger or smaller than the base unit. So before we talk about this, I want to focus on this powers of 10. And to do that, we'll need to understand some scientific notation. Scientific notation is a way to write very large and small numbers as a number between 1 and 10 multiplied by 10 raised to some power. So the steps that we take, and we'll do some examples in the next slides, is first you move the decimal point to the left or the right until the number is between 1 and 10, and then you count the number of places the decimal was moved to. If the direction of movement was to the left, that number becomes a positive exponent. And if the direction was to the right, then the exponent is negative. So let's look at some examples. Here we have 4,500 as our number. Our first step is that we want to take this number and we want to say here there's a decimal place, and we want to make this number between 1 and 10. So let's move the decimal and see how many count steps it will take. 1, 2, 3. So if we move the decimal place 3 spots to the left, we have 4.5, which is a number between 1 and 10. And then to express that as scientific notation, we say 4.5 times 10. And because we move the decimal point to the left, we put a positive number here. So 1, 2, 3 to the left means that we have 4.5 times 10 to the 3. We can do this for numbers that are small as well. So you can see that the decimal point is here, and we'll have to move the decimal place to make this number between 1 and 10. So let's try. 1, 2 to give us 6.7. We're going to stop here because that's a number between 1 and 10. And because we moved the decimal place to the right, we're going to give this a negative number, raise this 10 to a negative number. So our final answer in scientific notation will be 6.77 times 10 to the negative 2. So let's do some more practice. Here we can see anytime that you have a number and you don't see a decimal place, you can place a decimal or pretend there's an imaginary decimal place right after this last number. And so we're going to move this to a value that's between 1 and 10 again. So 1, 2, 3, and 4 to get 5.2. And because we moved this 4 spaces to the left, now we have this positive number. So our final answer is 5.2314 times 10 to the 4th. For this number here, we don't have to move it at all. The number is already small enough. It's between 1 and 10. You can express this number as 3.2 times 10 to the 0, but you don't have to do that. Now we have this very small number, so let's make it between 1 and 10. Let's move the decimal place, 1, 2, 3, 4, 5 to get a value of 4.28. And because we move this 5 spaces to the right, we're going to have this negative number here. So 4.28 times 10 to the negative 5 is our value. And one more example, We have this very large number here. Let's pretend there's a decimal place behind this 0 and move it to the left. 1, 2, 3, 4, 5, 6, 7, and 8. So we move the decimal 8 places to the left. So our answer is going to be 6.02 times 10 to the 8. Now, just like we can put numbers into scientific notation, we can take numbers out of scientific notation. So you're just going to do the reverse of whatever you did to put it back in. So here's one example. We have 5.2081 times 10 to the 12, and we're just going to move the decimal place 12 spaces to the right. So that's shown here. If you have a positive number, you move to the right, add zeros to the right. If you have a negative number here, you add zeros to the left. So for this example, we'll move it 12 spaces, 1, 2, 3, 4. And then when you run out of letters, you're just going to fill the rest up with zeros. 5, 6, 7, 8, 9, 10, 11, 12 to get our final answer. So take some time to practice putting some numbers into scientific notation and out of scientific notation. So let's go back to measurement. It's really important to know scientific notation because this is the way that we will express measurement outside of the base unit. So the prefix over the unit will tell you how large or how small. For example, let's look at gram, which is a measurement of mass. We have our base unit, which is 1 gram. Here in this table are some prefixes, and it tells you how many zeros you need to add to that value. So when we say we have 1 kilogram, we go up to the kilo chart and see that you have to multiply 1 gram times 10 to the 3. So if we take 1, pretend the decimal place is here, and put 1, 2, 3, we'll add 3 zeros, and that'll give us 1,000 grams. Now, in reverse, we can say we have 1 milligram, which is 10 to the negative 3 grams. And we'll just move the decimal place in the opposite direction. So we'll pretend that the decimal place is here, 1, 2, 3. That means we add 0, 0. And so this is our final answer, 0.001 gram. So what this is telling us that the kilogram is really large. And inside of 1 kilogram, we have 1,000 grams. The milligram is really small. So in one milligram, we have 0.001 grams. So definitely using that scientific notation to help express how big or how large something is. So let's do a knowledge check. Let's try to convert these values into scientific notation. Let's say that we have something and we want to convert this 2,309,105 into scientific notation. So this number, we need to make it between 1 and 10. 1, 2, 3, 4, 5, 6. So it'd be 2.309 times 10 to the 6. Now we're going to do this for this smaller number, and we're going to convert this to a number between 1 and 10. So 1, 2, 3, 4, 5, 6, 7. And because we move these to the right, we're going to give a negative value. So 6.08 times 10 to the negative 7th. And here are the answers shown on this slide. So now we're going to try to understand how we can apply this to measurement. So this is an example of a question that you might get on an exam, such as how many grams are in 96 kilograms and how many meters are in 10 centimeters. So let's look at our chart again. We have 96 kilograms. And when we talk about kilo, that means we need to add three um, zeros to this value. So 1, 2, 3. And then how many meters are in 10 centimeters? Centimeters is multiplying this by 10 to the negative 2. So we're going to take this value and 1, 2, move it to the left. And so the values are 96,000 grams. So we added those three zeros. And how many meters is 0.10 meters because we moved that decimal place -2. Okay, so that's going to summarize our chapter 1 on matter and measurement, and we'll do some more examples on measurement and scientific notation in class, on our Wednesday class. And now we're going to talk about atoms and the periodic table. So let's introduce ourselves to atomic theory. This theory aimed to answer the question, how small can we go? So if we were to cut up our matter into smaller and smaller pieces, just how small can we go and have the matter retain the chemical and physical properties that we discussed in chapter 1? And this is a question that the ancient Greeks pondered on. And even though they didn't really have an idea as to what an atom is to the level of what we know now, they did know that there was a limit where the matter would no longer retain its properties. So there had to be some thing that was small enough that you couldn't go any smaller. So that leaves us to John Dalton's theory. So it was the first complete attempt at describing matter using the law of conservation of mass. So this says that mass can neither be created nor destroyed. And he came up with the following proposition. He said that elements are composed of minute indivisible particles called atoms. Atoms of the same element are identical to each other and are different from atoms of any other element. When compounds are formed, the atoms combine to form a molecule, which we talked about in our last chapter, in which the number of each type of atom is constant. And during chemical reactions, atoms are rearranged, but the number and kind of atoms are unchanged. So based on that, we come up with these idea of the atom and these subatomic particles. So while the atom is the smallest particle that will retain the properties of the element, we can break it down into subatomic particles. It is the number of protons that is characteristic of a particular element. So when we think of this atom here, we can see that it is made up of protons and neutrons, and this little circle, this densely packed circle, which we call a nucleus. And this nucleus is surrounded by electrons. Protons have a positive charge, neutrons are neutral, and electrons hold a negative charge. And one atom has the mass unit of 1 AMU. It's so tiny that we had to make up a mass unit. And again, we're going to visit our friend scientific notation. It's so tiny that one atomic mass unit is 1.6033 times 10 to the negative 24 grams. So really, really tiny. And this is a summary of the charge and the actual mass and the relative mass, which is your atomic mass unit of each of these subatomic particles. So positive, protons have a positive charge, and it weighs 1.67 times 10 to the negative 24 grams. And it is the same mass of one atomic mass unit. A neutron is neutral, so it holds 0 charge. It also has a mass of 1.67 times 10 to the negative 24. It has 1 atomic mass unit, and electrons have a negative charge, and they're even smaller than a proton or a neutron. Their actual mass is 9.11 times 10 to the negative 28, and it has 0 mass. So most of the mass of an atom comes from its protons and its neutrons. So to summarize, protons and neutrons are similar in mass and are way larger than electrons. There is a dense region in the atom called the nucleus, which contains the protons and the neutrons, and the nucleus is positively charged because of those positive protons. And the electrons occupy a large region of space that surround the nucleus, and the electrons are in constant motion. So we're going to think about how we can identify one element from the other. Because the identity of an atom, and thus its chemical and physical properties, are determined by the number of protons, we have defined that number as the atomic number. We will refer to the atomic number as Z. And the atomic number is the number of protons, and that is also equal to the number of electrons in a neutral atom. So most atoms that we will encounter, unless otherwise stated, will have a neutral charge, meaning that the positives and the negatives, or the protons and electrons, are in the same amount. Because the bulk of the mass, remember, protons are much larger than electrons, of the atoms are made of the protons and the neutrons, we have defined the number of the protons and neutrons as the atomic mass. Because the electrons are so tiny, they don't contribute to any of the mass. So the mass number, which we'll say is A, is equal to the number of protons and neutrons. And this is important because we're going to use this information to look at an element and the information we're given on the periodic table and determine the protons and the electrons. So we'll want to familiarize ourselves with an atomic symbol. This is prescribed to each atom or element on the periodic table. You'll have this X. I'll show an example in the next slide. And this is on the periodic table. The mass number is A. And again, the mass number is the protons and neutrons because they contribute the mass to the atom. And then we have Z, which is the atomic number. In a neutral atom, Z equals the number of protons, and it also equals the number of electrons because the positive and negative charge need to balance out. Now, because we know what Z is and A is going to be the number of protons. Now we can do some math and figure out the number of neutrons because the neutrons don't contribute any charge. So we don't know yet how much they are. So if we want to figure out how many neutrons are in this symbol, we just take A minus Z, and that will equal our neutrons. So here is the periodic table, and you can see here the mass isn't shown on this periodic table, but you'll see the atomic symbol here. Hydrogen has H, and then this is the atomic number here. And typically the mass would be at the bottom. So let's do a knowledge check. Here we have our oxygen. The chemical symbol is 0, and we want to know how many protons, electrons, and neutrons are in this atom. So again, the atomic number equals the number of protons and electrons. The atomic number for oxygen is 8. So oxygen has 8 protons, and because the atom is neutral, the positives and the negatives need to be the same. So there are 8 electrons in this molecule as well. We want to figure out how many neutrons. So again, we're going to take the atomic mass and we're going to separate it, subtract it from the atomic number. So 16 minus 8 is 8. So in oxygen, there are 8 protons, 8 neutrons, and 8 electrons. So let's talk about the elements, what we saw on the periodic table. What we find is that matter of a particular type or a particular element behaves differently than matter of different elements. So oxygen will behave differently than an hydrogen. Each element will have characteristics that are unique to it and different from other elements, and those unique characteristics come from the arrangement of the subatomic particles within the atoms of that element. So now we're going to talk about how the electrons are arranged inside of an atom. We briefly touched on the fact that electrons are constantly in motion in this large space around the neutrons. So electrons do not orbit randomly around the nucleus of the atom. In fact, their negative charge and the positive charge on the nucleus lead to very distinct cones where the electrons can orbit. Remember, opposites attract. Opposites repel each other. So the electrons will repel each other, but be attracted to the nucleus. So you have this pull from the positive nucleus that keeps the electrons close to the nucleus. But then if you have multiple electrons around the nucleus, those negative charges will repel each other. And because of that, they orbit in specific areas at specific distances from the nucleus. So we'll see this in the next slide. So this again is the structure where we have 6 protons and 6 neutrons in the nucleus. And then we have these electrons that are orbiting around in these distinct shells. You can see that all 6 of the electrons are not all very close to the nucleus. They arrange themselves in these different shells, and we're going to talk about what that is. So first we need to talk about energy levels. The first part of our description of the arrangement of electrons is to put them in shells or energy levels. As the shells get further away from the nucleus, they become bigger and bigger. And because there's more space, they can hold more electrons. And so we designate the shell number using the letter N. So N can be 1, 2, 3, and 4. And as the numbers get larger, the energy level gets higher. So N is going to be our lowest energy shell. So here is an example. We have our nucleus in the middle, and we have one shell, and the first shell can hold only 2 electrons. It's pretty small, and these 2 electrons are going to repel each other. Next, we have the second shell, and the second shell can hold up to 8 electrons. And then we have this third shell, and the third shell is really large, and it can hold 18 electrons. Again, because electrons are all negatively charged, they repel each other. So even within a shell, they will be designated to subshells where they can exist. Each subshell will have a different shape and size, and thus will be allowed to hold different electrons. Same thing, as the shells get bigger, they will have more subshells. So the shell 1 will have less subshells than the shell 2. So just think of it as like a large box that we put smaller box in, and a smaller box in, and a smaller box in. We're now talking about that second level, which is the subshell. So our subshells are designated with these letters S, P, D, and F. And here on the right, you can see the maximum number of electrons. So the S subshell can hold 2 electrons. The P subshell can hold 6. The D subshell will hold 10. And the F will hold 14. So how does this relate to those big circles shells that we showed in the first slide? Each shell has a certain number of subshells that they can hold. Again, so N is our 1 is our smallest energy shell. It's the lowest energy. And because it is so small, it only has 1 S subshell. Now, if we go to our second subshell, which is larger, it can accommodate 2. So it can have S and P subshells. If we go to our third shell, which is larger than 1 and 2, we can now fit 3 subshells inside. So S, P, and D. And then for this course, we will hang out around the 4th and 5th energy shell. But for now, for the F, we'll have S, P, D, and F subshells. So back to our example that we showed in the previous slide, we'll kind of zoom in. So n equals 1. This is what we call our shell. If we zoom in, we can see that the first shell only has one subshell, which is S. When we look at shell number 2 and we zoom in, we can see that we have now two subshells, an S and a P. When we look at the third shell and we zoom in, we see now that there are three subshells, S, P, and D. And lastly, when we look at the fourth shell, the largest one here, it can accommodate S, P, D, and F subshells. So now we'll look at how we are going to express this as far as the number of electrons that this shell can hold. So for the first shell, remember, we can hold 2 electrons. We have one, which is the shell. We have our S subshell, and we can put 2 electrons into our S subshell. Always we'll have 2 electrons in it. Next, we'll go to our second shell, and the second shell can hold 8. Remember, the second shell has S and P subshells in it. So we can have 2 here in our S subshell, and we can have 6, always 6, in our P. 2 plus 6 is 8. When we go to our third shell, now we have S, P, and D subshells. S can always fit 2 electrons. P can always hold 6. And for D, we can put 10. So if we do 2 plus 6 plus 10, we get 18 total. And we're going to stop at the fourth shell for this class. So the fourth shell has all 4 subshells, S, P, D, and F. S, again, always holds 2 electrons. P will always hold 6. D will always hold 10. And F can hold 14. And so when we add up all 2 plus 6 plus 10 plus 14, we get 32 total electrons. And we're not interested in this class in G subshells. We're going to stop at F for this class, but you could go on. So let's talk about orbitals. Within each subshell, the electrons will occupy orbitals. So we have a shell level, we have a subshell, and within the subshells, again, another box, we have these orbitals. Each orbital holds 2 electrons. Electrons can coexist in an orbital because they will spin in opposite directions. And we won't get into that too much. We have a up spin and a down rotation. Charged particles spinning in opposite directions will generate opposite magnetic fields, but we won't need to go into the particulars for that. So here is just a summary of everything that we talked about, and just how many orbitals there are here. So we have our main energy level. We've been calling them shells. Then we have this sub-shell level, and then we have the number of orbitals. So because each subshell has can hold 2 electrons, for example, for our shell 1, we have 1 subshell, and we have 1 s orbital that can hold 2 electrons. That's why there's this maximum of 2 electrons that are there. For our second energy level, again, remember we can hold s and p orbitals. So we have 1 s orbital, which can hold 2, and then we have 3 p orbitals. So we have 2 times 3 is 6. And just like we did on that last slide, if we add 6 plus 2, that gives us a number of electrons that can be held in this subshell. For the third energy level, we have three, we have an S, a P, and a D, and you have one S orbital, so you'll always have the one S orbital, and you kind of just add on. We have 3 P orbitals, and then we have 5 D orbitals. And so you just multiply 2 times 5 is 10. Similar to this, 3 times 2 is 6, and 1 times 2 is 2. If you add the number, you get 18. And then for F orbital, you just add everything up that you had in these previous. So you have the 1s orbital, you have your 3p orbitals, you have your 5d orbitals, and you have 7 f orbitals. So that's why you can hold 14 electrons in this shell. And when you add up 14, 10, 6, and 2, as we did on our last couple of slides, you get 32. So this leads us to how we will visualize an element is through its electron configuration. And this is going to tell us a lot of information. It's going to tell us how many energy shells we have, how many subshells we have, the type of orbital that's being occupied, and the number of electrons. So the most simplest element on the periodic table is hydrogen. It has 1 electron. So when we talk about hydrogen in its electron configuration, it has 1 shell with an energy level 1. The first shell can only hold an S subshell, and it only has 1 electron. So even though the S subshell can hold 2 maximum, we only have 1 electron to put in. So now we're going to go through the steps of writing electron configurations, following these easy steps, and then we'll do some examples. The first step is to find the element on the periodic table and figure out the number of electrons. So we already discussed that the atomic number tells you number of the protons and the number of electrons. Then we're going to follow the yellow brick road and fill in the orbitals in that order with the number of electrons. That yellow brick road will be on the next slide. Make sure that all of your orbitals will be full. So you just keep adding electrons to that orbitals until you run out. And when you add up all the exponents, they should give you the number of electrons that the atom has. So you should get the atomic number. So this is the yellow brick road. This helps doing making electron configurations relatively easy. So let's use sodium as an example. This is the atomic number 11 for sodium. And so this means that sodium has 11 electrons. Now let's fill it in. So you follow the yellow brick road, meaning you follow the arrows down. So we have 11 electrons. We'll fill in our 1s2. So we've used 2. We'll write 1s2 here. Then we still have some more electrons. We have 9 left over. So we have enough to fill in this 2s2. So follow down. So we'll write 2s2. We still have more electrons, so let's keep going. We're going to start back up. We're going to follow the road and go to 2p6. And then we still have 1 electron left over. So we wrote 2p6. We still have 1 more. So we'll just fill in 3s1. So that's our electron configuration for sodium. Again, 1s2, start back at the top, 2s2, start back at the top, 2p6, and then we have 1 electron left over, which is 3s1. And that gives us our electron configuration down here. So here is just a general overview of our electron configurations based on location of the periodic table. So because there is a trend, you can see that everything on this left side of the periodic table will end in some type of S subshell. Here you can see, with the exception of helium, which is here, then you'll have this p orbital here. We talked about sodium, and that ends in this p orbital range here. And then we have this 3D, 4D, 5D. The Ds are here. So when you do the electron configurations, these elements tend to end in this D subshell. And then here on this bottom part are F. So there are some trends that you can see with the periodic table. And that leads us to some periodic trends, because based on the electron configuration, that will dictate how the atoms behave. So before we end our lecture, and we will touch on particularly a few of these trends in our next lecture, where we'll talk about chemical bonding and why atoms even need to form compounds, let's go over some trends. So because the electrons can dictate, and their configuration dictate characteristics of the atoms, we can talk about these trends. So one is atomic size. So essentially how large the atom is. And atomic size on the periodic table increases from right to left. So as you move from the right side of the periodic table to the left, the atomic size increases. It also increases going from top to bottom. And you can imagine that as you add on more of these energy levels, you get a larger size. And then, in addition to atomic size, we'll talk about ionization energy. So the ionization energy is the ease of removing an electron from the valence shell. So the valence shell electrons are electrons that are in that outermost shell. So when we talked about sodium, we ended in a 3s shell. And so that would be our outermost shell, and you can use energy to remove that. And when we talk about bonding, that will come into play. So when we're asking how much energy does it take to remove that last electron? And then we have electronegativity, and electronegativity is the ease of attracting a new electron to the valence shell. And this will all be put into some more context in our next lecture, as we talk about the sharing of electrons, and then also the gaining and loss of electrons. So electronegativity will be attracting. So ionization energy also follows some trends on the periodic table. As we move from the left of the periodic table to the right, we have an increase in ionization energy, meaning that it takes more energy to remove an electron. And then we see this trend increase as we go from the bottom of the periodic table to the top. So ionization increases as we go from left to right, and it also increases as we go from bottom to top. So a question that you could be asked on a quiz or an exam is, which has a larger ionization energy? Lithium, here, this Li, or carbon, the C? And the answer would be carbon, because as we go from left to right, the ionization energy increases. Lastly, we'll talk about electronegativity, and this increases in the same trend as our ionization energy. So electronegativity increases as you go from left to right, and as you go from bottom to top. So another question you could be asked is, which has a greater electronegativity? What element would be able to attract electrons more? Potassium here in K, or beryllium here with Br? And the answer would be beryllium, as we have increasing electronegativity going from left to right. So that is all that we have for today. In this lecture, as a recap, we talked about matter, how we classify that matter as a substance, a mixture, We talked about physical and chemical changes and the different states of matter. And we also talked about how to measure that and scientific notation um, for those measurements. Then we talked about elements and atomic theory. We talked about the components that make up an atom, protons, electrons, and neutrons. And we talked about how they're arranged inside of the atom. We then described how we can configure those electrons or where they live around the nucleus of an atom, and then some characteristics of the elements on the periodic table. Next week, we'll talk about some bonding that is dictated by the electronegativity and ionization energy.